Okay, so last video for today, Newton's third law. We're going to talk about this a little bit and then do a bunch of examples. This will probably be the longest video, I think, of the day. But Newton's third law is pretty simple. You've heard it before tons of times. For every action, there is an equal but opposite reaction. Now that's great. It tells us some things, but it doesn't really give us a good mathematical foundation to work with that we like in physics. So let's give it a mathematical foundation. That is, the force that object 1 exerts on object number 2 as a vector is equal to negative of the force that object 2 exerts on object 1. That is, for every action, there is an equal, so equal in magnitude, but opposite in direction. Every action has an equal but opposite reaction. So when we talk about force F1 on 2 and F2 on 1, these things are what we call a force interaction pair. Force interaction pair. This happens, these come about because two objects are interacting through some sort of contact force, for Newton's third law at least. Now, this means there has to be two objects. That's a bad 2, looks more like a Z. But there has to be two objects in contact for it to be a force interaction pair. So let's say I had a box with mass M1 and a second box, a little bit bigger, with mass M2. And I exerted a push force onto box 1. There's our situation, physical situation. Now, if I look at just box 1, so I'll draw another box number 1. If I look at it, it's going to have that push force on it. And we'll assume that we're on a horizontal frictionless surface. So we'll have a normal force up and a force of gravity acting down. And there's no friction on this one, again, for frictionless. You can see that maybe our normal force and our force of gravity are equal to each other. They cancel each other out. Actually, I'll call this N sub 1 for the normal force on mass 1 and Fg1 for force of gravity on mass 1. And they are certainly equal to each other and opposite of each other, but these are not what we would consider to be a force interaction pair, because our system here, is just the mass 1. We're not looking at mass 2, we're not looking at the table or the surface that it's on, we're looking at mass 1 only. And so the only thing that we see is force of gravity and the normal force acting on mass 1, and not two objects interacting. So normal force and force of gravity in general are not a force interaction pair. So N and Fg are not usually a force interaction pair. Now, it could be a force interaction pair, but we'd have to consider the table that this thing is on. So here's our table, maybe. And then we'd have to think about the mass of the table, M table, and maybe its acceleration, if there was any, or its velocity. We'd have to consider all these things in our analysis. And oftentimes, it's not really useful to do. But if our table was part of our system, the table would be exerting that normal force on the mass, and the mass would be exerting a gravity force or a pull down from that gravity force onto the table. And so that would be a force interaction pair, but in general, we don't do that. And so usually normal force and force of gravity are not force interaction pairs. However, if I were to look at my mass 1, actually, let's not do that. Let's draw a free body diagram. So if you remember, free body diagrams are just the dot that represents the center of mass and all the mass compressed there. So mass 1 would be this dot here, and it has a normal force, N1, on it, and a force of gravity, Fg1. I'm also exerting a push force on it, F push. And then something else is happening, but we'll get to that in a moment. On the other mass, I will have a normal force as well, N2, and a force of gravity, Fg2. And I know that this second mass will also be moving. Let's say I push mass 1, it causes the whole system of both masses to move with some constant acceleration. Well, I will know that there's some sort of push force being exerted on M2, but it's not my push force. It's not the force I'm exerting on the system because I am touching mass 1 and not mass 2. So what you have is instead a magnitude, or sorry, not magnitude, a vector that has some magnitude. We don't know what it is. We'll have to use Newton's laws to calculate it. But it has some magnitude and it points in the same direction as our push force. I'm going to call that force of object 1 acting on object 2. And that should hint to us that maybe we have this force interaction pair, and so what we should have on our mass number 1 is a backwards pointing force of F of object 2 acting on object 1. These F1 on 2 and F2 on 1, these are a force interaction pair, which I'll abbreviate FIP, force interaction pair. So that is a lot of how we do our analysis, at least the first part of our analysis for Newton's second law. From there, we'd have to relate things like the acceleration of the first object to the acceleration of the second object. Should be the same because they're in contact. They should move with the same acceleration. And then we could relate our forces, F of 2 on 1, together. And then if we had some friction forces, we could throw those in there somehow. But I'm not going to get too far into the Newton's laws practice and example stuff today, or at least Newton's third law, because I want to go through Newton's third law and then do some practice on the first and second laws. But it'll always have some sort of Newton's third law interaction that we need to deal with, especially if it's an object like hits a spring, compresses the spring, something like that. We'll have to deal with Newton's third law using to do our full analysis of that problem. So I'm going to go ahead and do a new page here, and what I will do on the next page is an example. So for example, and this is not going to be like a mathematical one. We're not going to calculate anything. This is going to be entirely just an intuitive, qualitative example. So let's say that we had mass 1 was 10 kilograms and mass 2 was 15 kilograms. I know I said it wouldn't have any numbers, but we're not going to actually do any calculations. We're just going to think about it and realize that mass 2 is bigger than mass 1. I exert a push force, F push, of 200 newtons in the positive direction on object number 1, which causes the whole system to accelerate at some acceleration A. And we want to know maybe what is the force exerted on object 2 by object 1. Well, to answer that question, we'd have to do a lot of thinking, but I do want to point out a couple of the finer points. How we would go about like figuring out where the forces point, all that stuff, we really need to draw some pictures, right? So here's my first picture. Well, my only picture. This is a picture. This is mass 1. Here's mass 2. Again, 15 or 10 and 15 kilograms respectively. And I exert my F push in this direction on object 1. I'll give it a coordinate system as well. So here's my positive X direction. My push force is in the positive X direction. Of course, my normal forces will be in the positive Y direction. Gravity is in negative Y direction. And this is a frictionless surface. So there's no friction that we have to worry about. So this is my picture that I've drawn. It kind of helps me out. It lets me kind of visualize what kind of situation we have going on here, but it's not really a great tool to use mathematically. The mathematical tool that we're going to need to use is called the free body diagram. And this is why we really want to draw these diagrams, because if I were to ask you something like, what's the force that 1 exerts on 2, you might have no idea where to start. But if we get an idea of where to start, we can often just try things and see what works. And that's what a lot of physics is trying something and seeing if it works. And if it doesn't, then going back and correcting, or maybe trying something new. So I'll have on my first object, so object number 1, first object, let me rewrite that. Object number 1. So my object number 1, I have my normal force N1 and my force of gravity Fg1. I also have that push force right here, F push, in the positive x direction. Positive x, up, positive y. I'm drawing my coordinate system now so that we know what direction is positive and which one's negative. And I don't have a friction force, so I don't have to worry about anything pointed in the negative direction for object 1. For object number 2, we'll have similar situation, a normal force, which I'll call N2 vector, a force of gravity pointed down, which I'll call FG2 vector. And then I'll have that push force, but not directly the push force. I will instead have F of object 1, so force that object 1 exerts on object 2. Notice how when it says F sub 1 on 2, it's drawn on object 2. So 1 on 2 gets drawn on 2. Force F of 2 on 1 will get drawn on number 1. The counter force that the other force, the force interaction pair force, F sub 2 on 1, will be on object 1, so on number 1, and it will have the same magnitude, but just in opposite direction. So this picture, if you just look at this, maybe you could kind of come up with an idea of what to do. You know about Newton's first and second laws. You know that these are unbalanced force pairs. And so, or sorry, not pairs, but these are unbalanced forces on both of these objects. And so we will see an acceleration, and we could use Newton's second law maybe to figure out what the acceleration is on block 1. Once we know that, we could figure out what the acceleration is on block 2, and then use F is equal to ma to solve for the force. Something like that, right? But that's not really important. I just want to kind of get you to see that in the beginning, when you first begin your problem in a dynamics problem, that is a force or a Newton's law type of problem, you should always draw a picture and then draw a free body diagram first. Make sure you include a coordinate system so you know what direction is positive and what direction is negative. Make sure that you include only your force vectors on your free body diagram. If I'm going to look at my picture, and let's say maybe I wanted to include my velocity vector on my picture, that's fine. If I want to include an acceleration vector on my picture, that's fine, but we do not include those on our free body diagram. So no acceleration, no velocity, only forces. With 3, no, tell you what, 4. I know it's a little pricey, but I'll give you the 4th exclamation mark. Okay, so that's kind of how we would start off our approach to a problem. But this is Newton's third law. I really want to focus more on the first and second laws today. So in the next one, we'll do some applications of Newton's first and second laws. So we will see you there.